In this video, we develop a way to identify redox reactions and distinguish them from other types of chemical reactions by using the concept of oxidation numbers. When dealing with redox reactions, a fundamental question we could ask ourselves is, how can we tell if a chemical reaction is in fact a redox reaction or not? Well, let's just remind ourselves what redox reactions are. They are chemical reactions that involve a transfer of electrons, where one or more substances loses electrons, and those electrons are picked up or gained by another substance or substances. And we will recall that we can use the oil rig mnemonic to remind us that loss of electrons is known as oxidation and gain of electrons is known as reduction. We can also recall that in an overall redox reaction, oxidation and reduction processes occur simultaneously. We can't have one without the other. We also learned in a previous video that reactions involving an acid with a reactive metal are in fact examples of redox reactions. And we saw that in this particular example, zinc metal loses 2 electrons to form the zinc 2 plus ion, and that the 2 electrons lost in that oxidation process were picked up by the H plus ions, 1 each, to form elemental hydrogen gas. Now this reaction is comprised of ionic substances, metallic substances, and molecular substances. And it is readily identified as a redox reaction by virtue of the fact that there are changes of electronic charges on particular atoms. But what about a reaction such as this, a reaction we've met before, the combustion of methane in the presence of oxygen to produce carbon dioxide and water? This combustion reaction is in fact a redox reaction. In fact, all combustion reactions are redox reactions. And this is despite the fact that this reaction only contains molecular substances. There are no ions, there are no net charges on any substance, and there are no observable changes of charge. And what about acid-base neutralization reactions? Again, reactions that we've met previously. It turns out that these reactions are not redox reactions. They are in fact what we call proton transfer reactions. And what about acid-carbonate reactions, which produce a salt, carbon dioxide plus water? It also turns out that these reactions are not redox reactions. They are also proton transfer reactions. And what about acid plus sulfite reactions, which produce a salt plus sulfur dioxide plus water? It also turns out that these reactions are not redox reactions, but are proton transfer reactions. And yet, as we've seen, reactions between an acid and a reactive metal are redox reactions that involve electron transfer. So this takes us back to our question, how can we tell if a chemical reaction is in fact a redox reaction? How can we tell if electron transfer has occurred? And if so, how can we identify which substance is the oxidizing agent and which substance is the reducing agent? We do this by assigning oxidation numbers to atoms within substances in chemical reactions. If the oxidation number of an atom changes during a chemical reaction, then that atom has undergone either oxidation or reduction. So in the case of our acid plus zinc reaction, we have already noted a change in charge occurs for both the hydrogen and zinc atoms, with zinc atoms changing from 0 charge to a charge of +2, and hydrogen atoms changing from a charge of +1 to a charge of 0. It turns out that these numbers, these charges, refer to the oxidation state of an element, and the numbers themselves are referred to as oxidation numbers. The oxidation number of an atom in a substance is defined as the actual charge on an atom if it exists as a monatomic ion, or we assign a hypothetical charge to an atom in a substance by simple rules. And here are these rules. Rule 1 applies to elements. The oxidation number of atoms in their elemental form is always 0. So in our previous example, we identify zinc metal and hydrogen gas as being elements, and so they both have oxidation numbers of 0. Rule 2 applies to monatomic ions. The oxidation number of a monatomic ion is the charge on the ion. So in our previous example, we identify the H plus ion as a monatomic ion, an ion containing only one atom, and its charge is +1. Meaning its oxidation number is also +1. We also identified the zinc 2 plus ion as a monatomic ion with a charge of +2, so its oxidation number will be +2. Rule 3 is about oxygen atoms within compounds. The oxidation number for an oxygen atom in most of its compounds is -2. The only common exception to this rule that we need concern ourselves with is the compound hydrogen peroxide H2O2, where the oxidation number of oxygen is -1. Rule 4 is about hydrogen atoms within compounds. The oxidation number for a hydrogen atom in most of its compounds is +1. The only common exceptions we need concern ourselves with are metal hydride compounds, such as sodium hydride, where the oxidation number of hydrogen is -1. Rule 5 is about halogen-containing compounds, that is, compounds that contain fluorine, chlorine, bromine, and iodine. The oxidation number of fluorine is -1 in all its compounds. The oxidation number of all the other halogens, chlorine, bromine, and iodine, is also -1, except when they are involved in binary compounds with oxygen or another halogen above it in the periodic table. Now, this rule appears on the surface to be a bit complex, but in the next video we will see examples of how this rule and other rules apply in more detail. Rule 6 applies to compounds in general. The sum of the oxidation numbers of all atoms in a compound is 0. And Rule 7 applies to polyatomic ions. The sum of the oxidation numbers of all atoms in a polyatomic ion equals the charge on the ion. And as I said, we'll get a bit of practice applying these rules in the next video. But for now, let's look at how they apply to two chemical reactions we are already very familiar with. The first represented by this equation here, where H+ ions from an acid react with a reactive metal, in this case zinc, to produce the Zn2+ ion and elemental hydrogen gas. If we start with elemental zinc on the left-hand side, we can apply Rule 1 and assign it an oxidation number of 0. By the end of the reaction, we see that elemental zinc is transformed to the monatomic zinc 2+ ion, and applying Rule 2 for monatomic ions, we can assign it an oxidation number of +2 on the right-hand side. This means the oxidation number of zinc has increased from 0 to +2. If the oxidation number of an atom increases during a chemical reaction, that atom is said to have undergone oxidation. And it's important to remember this. An increase in the oxidation number for an atom going from the left-hand side of the equation to the right-hand side of the equation means that that atom has undergone oxidation. Let's now focus on the hydrogen atoms on the left-hand side. They appear as monatomic H+ ions, and so Rule 2 applies, and we assign an oxidation number of +1 to these hydrogen ions. After the reaction, we see that the hydrogen atoms appear as elemental hydrogen, and so we apply Rule 1 and assign an oxidation number of 0 to both hydrogen atoms. We now note the oxidation number of hydrogen has decreased from +1 to 0, going from left to right. If the oxidation number of an atom decreases in a chemical reaction, that atom has undergone reduction. And so we see that by assigning oxidation numbers to each atom in a chemical equation, we can determine which chemical substance has undergone oxidation and is therefore the reducing agent, and which substance has undergone reduction and is therefore the oxidizing agent. If we go back to our combustion reaction of methane plus oxygen producing carbon dioxide and water, we can identify the element in this equation as elemental oxygen, and via Rule 1, assign these oxygen atoms an oxidation number of 0. So that's an easy one. Still on the left-hand side, we note that hydrogen is in a compound with carbon, and via Rule 4, we assign hydrogen atoms in methane an oxidation number of +1. And then, by applying Rule 6, we can calculate that the oxidation number for carbon in methane is -4. And we can show our working on the right-hand side, where we see that the unknown oxidation number of carbon in methane plus 4 times the oxidation number for hydrogen, which we know is +1, has to equal 0, since according to Rule 6, the sum of oxidation numbers for all atoms in a compound must be 0. And we therefore calculate the oxidation number of carbon in methane to be -4. And so, at this point, we have assigned oxidation numbers to all atoms on the left-hand side of the equation. We now need to do the same for the right-hand side, starting with oxygen, where we see on the right-hand side that oxygen atoms are involved in the compounds carbon dioxide and water. And via Rule 3, we can assign oxidation numbers of -2 for all of the oxygen atoms on the right-hand side, meaning that the oxidation number for oxygen atoms has decreased from 0 to -2, indicating that oxygen atoms have undergone reduction. For the hydrogen atoms, we note that they are involved in the compound water on the right-hand side, and according to Rule 4, we can assign an oxidation number of +1 for these atoms, meaning that no change has occurred and the hydrogen atoms have not undergone any oxidation or any reduction. Lastly, we note that carbon is involved in the compound carbon dioxide on the right-hand side, leading us to assign it an oxidation number of +4, which we calculate according to Rule 6 by understanding that the unknown oxidation number of carbon in carbon dioxide plus 2 times the oxidation number for oxygen, which is -2, has to equal 0. The oxidation number for carbon in CO2 is therefore +4. The final point to make is that since the oxidation number for carbon has increased from -4 to +4, the carbon atoms have undergone oxidation. The end result is that oxygen has caused the oxidation of methane, or more specifically the carbon atoms of methane, and during this process oxygen was itself reduced, and it is therefore the oxidizing agent. Conversely, methane, or more particularly the carbon atoms in methane, have caused the reduction of elemental oxygen. The methane was itself oxidized, or at least the carbon atoms in methane were oxidized, and so methane is considered to be the reducing agent. In the next video, we look at more complex examples of calculating oxidation numbers of atoms within compounds and polyatomic ions.